Hello. I think today I'm going to present what I'm doing on the 3D printing, and I graduated as MD, and I I did not go into practice medicine, but I'm very interested in since my master is in neuroscience. I'm very interested in the molecular level, on the molecular level, how an anatomic structure uh, react and connect to each other. The basic question on the muscle contraction is we established the model 60 years ago. MIT does establish the single sarcomere, how single sarcomere contract. If you look at this as a Z9 and this as a M9, um, and that the action they taking between the actin and the myosin, and when uh, when a myosin drag actin into drag 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 um, um, when myosin drag actin into uh, its its structure, and basically it shortens the length of the sarcomere. But there's a problem because the current model we have only can explain. Um, oh, I hate this. Because the current model we have right now only can explain uh, how single sarcomere, if you look at this as a Z9, this M9, and both sides, both sides from both sides come in to M9, and with muscle, hence the one single sarcomere would contract and become shortened. There's a problem how this spatial relationship between the actin and the myosin relate to each other. And the traditional model we had that drawing um, the other half of the myosin would other half of the actin would directly um, uh, to knock into each other. That's apparently that's not true because you can see here um, that when it contracts, the Z9, if let's say like the number we get is three times. A sarcomere can contract three times of its length, shorten, and then the Z9 has to be on here at least on this line. So at the end of the A band, it's not. So basically, what is trying to say is that if you what I'm trying to say is that the actin has to be able to cross the M9. So once the actin crossed M9, you have a problem that how the other side of the actin spatially in 3D setting would be organized according to this side of the actin. So if you have direct um, spatial relationship one by one, you would run into each other. There's no way you can come cross to each other, and with the myosin in mind. Remember that in the space, besides actin, there's also myosin. So the actin itself has to be within a different spatial relationship as myosin, and with different relationship across the M9 with that site, that side of acting. So I hope that people, this is for the people who have the knowledge, know what I'm talking about. If you don't have the knowledge, you have to go back to revisit what is Sarcomere about. Oh, had this been said, there's a not. If you look at this Z9 here, here comes another question. Like right now, I need to figure out. This is the stage I'm in. First, I print out 3D print out spatial relationship that we have right now, and I don't have the model as in school. Then I come down to details on the actin and the myosin, trying to figure out what is the spatial relationship between them across the Z9 and across the M9. And on top of that, or just what I said before, that the actin has to be in different relationship with the myosin in order to be able to go inside of myosin structure. And on top of that, it has to be in different spatial coordinates with the other side of the M9, so that it would the actin from the other side of the M9 to cross the M9. And another constraint is that we have this side of the spatial relationship on this side of the myosin itself. Across M9, there's another spatial relationship different from this. I wouldn't say different from well, it has to be different, because that's if you have a different myosin, a different action structure, it means that it's different myosin structure. Oh, it's different actin structure, but same myosin structure. Could that be the case? Could be. Very well, could be. That means that across the M9, the spatial relationship between this side and that side for myosin is the same, but somehow the spatial relationship of the actin is different. I'm trying to do that with this model. Turn out very fragile and lost half of the actin. However, right now I'm doing is in school is really trying to put all these three together, uh, so that I would have a clear understanding on how cross the M9 and the Z9, how the uh, how this actin and the myosin interact with each other. This is not in the textbook, and this has been explored in many research papers until recently. But however, I haven't seen one research paper would come up with a model that fully explain how this spatial relationship to each other. There's underlying assumption that on the molecular level, things are different. However, what I'm trying to do is that even though they might be on the 3D setting different from the ordinary structures we can see on a cellular level, but they are still guided by the general physics. It has to be in a space, even in the molecular space, sorry about my pronunciation, molecular space, it has to be a spatial relationship that guided the muscle contraction. This is a very basic theory of ours, and which haven't been answered fully to its it deserve to be answered fully, because all these spatial relationships does eventually tell a story how our muscle contracts. And this is stage 2. I'm on stage 3 now. So I'm trying to once I determined their spatial relationship roughly, and which I can print out, and what I'm trying to do is that let's print out the molecular, so that at least we have something at hand that would tell us what it is. So I tried multiple approach, and can see the field fragile structure. But by in the process of doing so, there's a lot of understanding I made on how this actin and myosin, triple myosin, how was their role play into this. For example, in the embryo, not in the muscle developing stage, it is our understanding that actin, also our observation, that actin has to be in place for myosin to drop in to their orbit, to their space. Why is that? It is, if you look at my parametric drawing or parametric stimulation running in the computer program, I understand that, because in the 3D settings, without all these guidelines from the actin, there's no way you would be able to drop in. You cannot just put the myosin in a space, in a 3D space, because it won't fit. It won't connect to each other. here's why I'm trying to explain. See, if you look at the relationship between this actin and myosin, this is a myosin, and what connects actin and myosin is the myosin heads. Myosin heads has to be in a specific angle so that it would be able to pull myosin actin in, and it is very crucial that you have this 3D structure to define the 3D space with 3 actins before the ones in the middle. See, before let's see this way, before the myosin comes in, so that its head would be in a specific spatial relationship with the actin. And there's also detailed calculations on why myosin and actin, when we develop muscle system, the actin has to be there. And I have a short video. I would show you in the video when I do the 3D parametric program, how that tells the story on why it has to be 3 actin molecular in place before the myosin molecular would be able to be in place. Okay, this is a bigger version. However, it's too fragile to be able to keep its all the myosin head. What I found out is that during the making of this molecular model, the most fragile part is the head, and the head has to be able to move. So far, right now, it's not being able to move in. I gotta make a model that will make it move. And but this definitely gave us a research tool that if we put everything together, of course, it should be in the same size. Right now, I'm making more, and you see that because actin to actin has to be in a specific direction so that they would come across each other without bumping into each other. And the traditional model would be this, in between this would be Z9, and this won't work because they're gonna bump into each other. I'm sorry, this would be M9. Traditionally, this should be M9. No, I'm doing it wrong. Sorry. So let me do this. If I put it here, so I won't be, put it into my hands. It's gonna be hard to keep it in shape. Okay, so just ignore that there was wasn't supposed to be the mouse is supposed to be staying in place. This is M9. Just say let's move the M9 here. Just look at the actin structure instead of looking at the just for example, I just want to show the actin structure, how they come to each other. See, when they pull, this comes here to the M9, and this guy has to be able to cross M9. That traditional, I wish I would have two of them. Traditional would model would say they would go hand in hand. They would go like head to head. They would bump each other. There's no way you can cross the M9, and so there's a spatial relationship specifically can be made so that they would not be. I think it's like this one to this one, and this one to this one. Yeah. So the axis of this. Let me do this way. Just ignore that. I'm not trying to confuse you, but it would be better to illustrate this. If I have more, I'm printing more so that see the axis would be this axis, the ones here. So this guy's axis would line up with this axis, and this axis would line up with the mousing axis here, and that's not in the spatial relationship. So the mousing would be able to drop in. That's for the muscle development. But however, this way it would go into each other. See that? It would be able to go into each other. So that's how the muscle contract should be. What I'm trying to do is to print out all this molecular so that I would be able to put them together in the 3D settings that eventually we would be able to figure out what is what and how this spatial relationship connect to each other, how they would be able to cross the M9 and be able to make that muscle contraction possible with their how they situated in the 3D settings. So that's my goal, and trying to make this into a business. I think I have something to new to offer here, and it would be my goal that how exactly a Sarcomere contract and make sense. And in school, I always have these thoughts that how does this how does this have direct um, contradict to each other. This side mouse, and if the muscle has to contract, this is M9, say this is A9, and the actin would run across the M9, and the other side of the mouse, and if this structure is exactly identical, the actin, when they run across the M9, they would run into each other. And it's never been answered in our medical school and in anatomy class. That simply anatomy instructor just stopped here because that's not part of their responsibility, I guess, to talk about how on the molecular level how this Sarcomere structure would work. However, they're still using Sarcomere as a basic unit for muscle contraction. But this contraction this contraction needed is that when they contract, they has to be able to cross the M9. And when they cross the M9, the actin structure would run into each other. There must be a specific spatial relationship there for a single Sarcomere be able to work. I will keep this as a topic, and I will update my progress. Thank you.